Hi, everybody. This is Miss Weeson, and we are getting ready to start Unit 8 in AP Chemistry. And as you can see from the title of the notes, that is our acid and bases unit. So let's go ahead and pull out your note guide and title it Unit 8. I would also recommend you pull out anything else that you may need to help you get through these videos, such as scrap paper, your calculator, your AP reference sheet, etc. Now, I just want to give you a fair warning that when we get into the quantitative portions of acid and base chemistry, you're going to see a lot of the similar concepts that we learned in equilibrium. In other words, the techniques of using the ICE diagrams or the Rice diagrams are also going to be applied here in this unit. So I just wanted to give you a fair warning. I'm also hoping that you actually had some type of introduction to acid and base chemistry in your first year chemistry class. Now, acids and bases are super important. So many applications, okay? They are in everyday life. We are using acids and bases in our homes. We're using them as a part of our cleaning materials, our cooking materials. We see that acids and bases are used in large-scale industries. We even see that acid and base chemistry comes into play quite a bit in biological organisms. So super important here. Now, where did they get the word acid from? Acid is literally a Latin word, acidus, and it translates to meaning sour. The other term is alkali or alkaline, and this basically is a base. And so if you want to, you can just title it alkaline. We would also say base or something like it that is basic. Okay, so I really want you to get used to the interchange of words here. Now, bases are interesting. They feel slippery to the touch and they taste bitter. And you know this when you wash your hands using hand soap. It's very slickery. So again, a lot of substances that are acidic and basic are used in your homes. Now, the word alkaline comes from an Arabic word that refers to the ashes of certain plants that were burned, okay? And so in chemistry right now, I do want to give you a heads up that before we get started, a lot of you will write water as H2O. Another way to consider writing water is HOH, okay? And you'll see that this actually helps you understand that water is indeed hydrogen protons as well as hydroxide ions or anions. And so if you kind of keep that in the back of your head, it might help you understand some of these definitions that I'm going to explain here. So let's take a look at the three primary definitions of acids and bases. Now, they are going to go in order from, most limiting to the most comprehensive. And so this first definition here is Arrhenius. Arrhenius, okay? The Arrhenius theory suggests that acids are going to be something that donates a hydrogen ion in water. Now, I want to be very clear that when you talk about a hydrogen ion, you are talking about a hydrogen atom that has lost its one and only electron, hence H+. And so synonymously, oftentimes we will call these hydrogen protons. Okay, so again, there's just some concepts here that if you didn't know specifically, it might hold you up and confuse you. So anyway, back to it. Acids are going to donate this hydrogen proton in water, and bases are going to donate a hydroxide ion in water. All right. Now, this is a very limiting theory. Let me explain why. If you take something such as ammonia, and for those of you who don't remember, ammonia is NH3. Okay, did you know that NH3 is actually a weak base? And if you look at the definition of Arrhenius, you're thinking, well, NH3 doesn't have a hydroxide to donate. And let me just show you what's going on here. If we mix ammonia in with water, okay, to make a weak base solution, what's going to happen is a hydrogen coming from water is going to rip off and ammonia is going to pick up that extra hydrogen proton to form NH4+. And then look what remains. Since we stole that hydrogen from water, we now have a bunch of hydroxides floating around. And so the ammonia is a weak base, even though it doesn't have hydroxide ions. Now, what is a Bronsted-Lowry definition of an acid and base? This is basically designating an acid as something that's going to donate a proton in water, whereas a base is going to accept a proton in water. Again, this is a little bit better of a theory. It's more comprehensive. It actually allows us to explain how ammonia is a base. If you take a look at the reaction up here that I drew with ammonia, and we're saying, well, ammonia is a weak base. Well, look at the definition of what Bronsted-Lowry says. This is going to be something that accepts a proton. And you can see here that from the reactant side to the product side, that is indeed what has happened here. Ammonia took on what I really don't want you to think about here when you're talking about Lewis definitions. So let's go ahead and take a look at Lewis definition really quick. This is indeed the most comprehensive. What an acid is, here's and how this one is according to Lewis. The other two are talking about protons, where the Lewis definition completely does an about face and literally defines acid and bases in terms of electrons or electron pairs. Now, I want to remind you, when we talk about an electron pair, okay, we learned in previous units that a pair of electrons would be equivalent to one bond, okay? Look at what it says. It says an acid accepts an electron pair and a base will donate an electron pair. Now, this is not, I'm not talking about the movement of electrons in a redox sense here. I'm actually talking about actual bonds forming or breaking, okay? Because an electron pair, when you hear that word, it's referring to bonds, because a pair of electrons equals one bond. Now, Lewis's most comprehensive definition of acids and bases goes beyond that of Arrhenius and Bronsted. And, you know, if you want to, you can even look at the example that we've been looking at here, this ammonia molecule, and how we've considered it a weak base. Well, let's take a look in terms of the Lewis definition of this reaction. Now, one thing I think would help highlight here is if I actually drew the Lewis dot structure of ammonia. And when I do so, I notice that there is this lone pair of electrons on the central nitrogen. Now, one of the things when you throw this in water, you know you're going to have H plus and OH minus ions. Interestingly enough, notice that this hydrogen here does not have any electrons to share. But what does have electrons to share? That's right, this lone pair here sitting on the nitrogen of the ammonia molecule. And so what that lone pair is going to do, because those are electrons, they're going to be highly negative in this area, and they're going to be really attracted to the positive charge of the hydrogen protons that occur when water disassociates. And so ultimately, just like we showed up in the balanced reaction above, this hydrogen proton is going to attach itself to the ammonia molecule, okay? And it's going to form something that looks like this. And we call this ammonium at this point. And so anyway, you can see here that the Lewis definition is actually defining acids and bases in terms of electrons and not protons. And this, again, will define and explain all of the traditional acids and bases we find on our planet. It also will explain acid and bases in terms of other types of compounds that we might not actually think are acids and bases. And we call these coordinate compounds or coordination compounds. And be aware that when you get into organic chemistry, they're going to predominantly use the Lewis definition to define acids and bases. Okay, so we're going to really just kind of focus on the Bronsted-Lowry concept of acid and bases. And one of the things that I want to cover before we move on, and by the way, this is going to help you understand how to write these acid and base equations. This will help you identify what your acid is versus what your base is. And so this is probably going to be a new vocabulary term for you, but you are going to need to be able to identify the conjugate acid and base pair. And if you look at the definition of what conjugate means, it literally means pairs, okay? And so I have a couple of examples here in the notes, and you'll see hopefully after a couple examples what I'm talking about. But the definition is stating that a conjugate acid and base pair is a pair of compounds that differ simply by the presence of a hydrogen proton. Okay, super important to understand conjugate acid base pairs, especially when we get towards the end of the unit talking about our buffer systems. Okay, and so look at equation, this first reaction here. We have nitric acid and we're throwing that in with some water. Now take a look at what happens after the reaction occurs. By the way, you'll see that below these substances, I have Ca and Cb. Ca just simply means conjugate acid, and you could probably guess what Cb means. That's right, it means conjugate base. And so jot those down if you need to. So what's going on here? What I notice on the reactant side with this first reaction is that I have my acid, which is nitric acid, and it looks like what is going to happen, and you see this on the right side, you see this on the product side. It looks like this hydrogen proton from the acid is going to go right into water. Okay, look at what happened here. When the reaction was over, that simply means that I am now just left with my nitrate ion. Where did the hydrogen go that was bound to it? Well, look, it looks like it was added to water. And so this is when I would like to introduce to you guys a substance called the hydronium ion. Now, this is basically a hydrogen proton piggybacking off of a water molecule. Okay, so water is going to act as a base in this first reaction. You could see here, water is going to act as the base. And why? Because it's going to accept the hydrogen proton. And when it accepts the hydrogen proton, it forms a molecule we call hydronium, H3O+. Now take a look at your Bronsted-Lowry definition. If an acid is going to donate a proton in water and the base is going to accept the proton in water. And so go back down here. You can see the acid is going to, again, donate the proton and the water is going to accept the proton. And so in this particular example, our acid, HNO3, will form its conjugate base, okay, NO3 minus. And the base here, which is water, is going to form its conjugate acid. All right. So again, what is an acid base pair that is dealing with its conjugates? It's simply a pair that is differing by the presence of a hydrogen proton. Look at the second reaction. NH4 plus in the presence of water, and look at what it's yielding. It's responsible for producing hydronium and, oops, I forgot to add a plus sign in here, you guys, and ammonia. So in the left, on the reactant side, the ammonium, the NH4, is going to act as our acid. And now what would the conjugate base be? Well, if it's an acid, and remember, it's going to donate a proton. So this acid should strip off one of those hydrogens, right? And well, indeed it does. And so after the reactions occurred, that you could see this acid here has lost a hydrogen proton to form its conjugate base. Okay, now let's look at the water, which is acting as a base. And according to the Bronsted-Lowry definition, the base is going to be the thing that accepts the proton. All right, and again, one more time, you can see that it has, and it forms, again, the hydronium ion. One more example so you can kind of see the idea of conjugate acids and bases. We have H2PO4 minus and water. And in this particular case, we're going to result in hydronium and HPO4 2 minus. Can you identify the acid and the base here? Consequently, can you identify the conjugate acid and the conjugate base? So if you said that H2PO4 is going to be our acid, because look at what's happening, you guys. This acid is going to lose a proton to form the conjugate base. And if you look at water, it is behaving as a base. It is going to accept the extra hydrogen to form the conjugate acid. Now, you guys, water is not always going to behave as a base here. It just so happens in this example, that is what is going on here. So in each of these examples, notice how we form that hydronium ion I keep talking about. Now, in all of these cases, you will notice that each of these reactions produced the hydronium ion. And really all that is a water molecule picking up an extra H+, okay? And remember that highly electronegative oxygen atom in the water molecule makes and has an affinity towards the positive proton to form H3O+. Now, I'm going to let you know this hydronium ion is considered to be the same as H+, okay? Now, that is because H+ is joining to the water molecule. And so the hydrogen proton, it cannot exist in aqueous solutions. It's always going to piggyback on a water molecule and be written as H3O+, okay? So please be very clear that oftentimes the hydrogen proton, which determines acidity, right, is the same thing as the hydronium ion. A couple more examples here. Look at the next page on the top of page 2. I had a little Lewis dot structure of water and hydrochloric acid, and it's going to yield hydronium and chloride ions. So remember to Bronsted-Lowry, the acid's going to donate the proton and the base is going to accept the proton. So by virtue of that, what would you say is the acid and base, and what would be the conjugate acid and the conjugate base? So if you said that in this particular picture, water is going to be acting as our base and hydrochloric acid, HCl, is going to be acting as our acid, then you were spot on. Now, why is that? Notice that the base, it actually accepted the hydrogen to form hydronium. And so consequently, that's going to be our conjugate acid. And then, of course, you said the hydrochloric acid was the acid. It's going to donate the hydrogen proton to form the conjugate base. So the chloride ions, the conjugate base. Let's do a little switcheroo here. Let's look at some examples where water is going to act as the acid. And so in the next example, if you guys want to just number these, that way I have a reference point. So if you look at number 5, you'll see that water, I told you guys, is going to act as the acid in this case. And remember, when an acid is going to donate the proton. And so you can see here that when the reaction has occurred, that water was stripped of a hydrogen proton to form the hydroxide ions. And so hydroxide would consequently end up being the conjugate base. Now, ammonia is going to then act as our base. And since it's accepting the hydrogen proton, then the NH4 plus would be the conjugate acid. Okay, let's do a couple more really quick. CO3 2 minus in water yields HCO3 minus and hydroxide ions. Again, water here is going to act as our acid. It's going to strip that hydrogen proton to form the conjugate base. And conversely, CO3 2 minus, this carbonate ion, is going to act as the base to accept the hydrogen proton. And so this would be our conjugate acid over here. And I didn't leave much space for you to write here, but our PO4 is the base. Remember, our bases are going to accept protons. You can see that it accepts it over here, so that becomes our conjugate acid. And again, water, for the last time, is our acid. It's going to strip off that hydrogen to form hydroxide to form the conjugate base. Okay, so hopefully you're kind of comfortable going back and forth. In these last 3 examples, notice the formation of hydroxide ions. This would be an alkaline solution. So the big key here is, after going through these, hydronium ions versus hydroxide ions. Okay, let's go ahead and do the first example, which is basically a continuation of what we just did. Okay, in exercise 1, the first problem, it wants us to, actually it looks like all of these we are being asked to identify the conjugate acid and conjugate base. And so here on this first one, we have a reaction, HBr plus NH3 yields ammonium and bromide ions. Okay, remember, ask yourself, which one of the reactants, which one of these species is going to donate a hydrogen proton, and which one's going to accept one? Okay, and if you look really quickly right here at the HBr, it looks like it's going to give, the hydrogen proton. And consequently, if you look at ammonia, it looks like it is going to take on that hydrogen, okay? And so consequently, you could say that then HBr is your acid, and the bromide ion would be your conjugate base. And the NH3 is your base, where NH4 becomes your conjugate acid. All right, in B and C, notice that they did not give us a chemical reaction here. Now take a look at B. It's asking us what is the conjugate base of H2S. Now this reaction is not written for us, but we always need to keep in the back of our mind that this is aqueous and dissolved in water. So the best way to write this would be H2S and H2O. And then you're going to ask yourself, all right, what is going to happen here? Now, remember your water molecule has that highly electronegative oxygen and probably would love to borrow one of these hydrogens here. And so you'll form a hydronium ion, and then you will have HS, but since you got rid of a hydrogen proton, this would be a minus. And so this would be your acid, and consequently over here would be your conjugate base, and then the water would be your base, and the hydronium would be your conjugate acid. Okay, last but not least, and we actually answered more than we needed to, but we covered it all here. Now, NO3 minus, again, this is happening in water, so we would need to put water here to see where our protons are coming and going. And notice this negative charge here on this nitrate ion. It will desperately want some positive charge. So my guess is it's going to take the hydrogen from water to form hydroxide, and then that is going to pick up a hydrogen, that NO3 minus will, to form HNO3. So this would consequently be your base because it's going to accept the hydrogen, and then that would be your conjugate acid over here to the right. And the water is going to act as your acid, and the OH would be your conjugate base. So at this point, you should have noticed that anytime we write the formulas for acids, we always are going to write that hydrogen first. And so we should just clarify right now that some acids will only have one hydrogen to donate, and we call these monoprotic acids, okay, mono being one. An example would be, as you could see here, this acetic acid. Be very clear, it is the hydrogen that I just circled that would break off. That's the donating hydrogen. It's not the hydrogen that is a part of the polyatomic. Be very clear. Another example would be like HCl, hydrochloric acid. That would be a monoprotic acid. A diprotic, you probably can guess by the prefix here, di meaning two, are acids that will have two donating hydrogens. And you can see there's an example. Another one would be sulfuric acid, H2SO4. And then lastly, and not as many, but there are other polyprotic acids that would actually have more than two hydrogens that it could donate. An example would be, as you could see here, this phosphoric acid. And just like polyprotic acids, there can be polyprotic bases. And remember, according to Bronsted-Lowry, a base is going to be anything that can accept one or more hydrogens or one or more protons. So in this case, you can also make the assumption that there are indeed polyprotic bases. Now, we're going to talk about this next definition in a little bit more detail later, but the word amphoteric should be put onto your radar right now. This is a molecule that is going to behave or act as either an acid or a base. And you have already seen some examples where water has done that. So yes, water is indeed an amphoteric molecule. Now, like I said, we'll talk about this in a little bit more detail coming up. As example 2 is going to ask us to simply just write the dissociation or the ionization reactions for, it looks like a couple of different acids here. Now, it's asking us to leave water out, so omit water. It is important to know that each of these reactions are occurring in water, but we're going to leave water out. And so what we're going to do here is let's just do a couple of them. I'll do A, C, and E, and then you can do the others on your own. One more time, I'll encourage you to pause the video and try it yourself before watching me. Now, we're going to just show the separation of these acids, again, without water, to show how they ionize or how they separate into their ions, because that's what dissociation means. All right, let's take a look at hydrochloric acid. Now, hydrochloric acid is going to separate into hydrogen protons and chloride ions. You see here that I drew the arrow in one direction, and there is a reason for that, and that is because hydrochloric acid is a very strong acid and will actually disassociate almost 100%. And when it does so, it's not going to reform back into the hydrochloric acid molecule, okay? Ammonium, this one is actually a weak acid. And what we're going to show here, again, leaving water out, I'm going to draw a double arrow. And you'll find out a little bit more later on why weak acids and weak bases, we would draw these double arrows here. Anyway, it would go back into the weak base, the ammonia, and that extra hydrogen proton would be floating around. Now take a look at this very last one here. This is a coordinate compound. Now, you wouldn't know that. I can tell because of this aluminum here. And if we were to actually take some of this aluminum, hydrated aluminum 3, so what's going to happen here is going to be a double arrow, and we are going to need to break off a hydrogen from this molecule somehow. Well, the hydrogen is going to come from one of these water molecules. You can see that this coordinate compound has 6 of them. And so remember, again, water is H plus and OH minus. So if we snap off a proton, a hydrogen proton there, what would remain? We would have aluminum, and we would have H2O, but there would only be 5 in this case. Do not forget we still have a hydroxide ion. Let's go ahead and put that in parentheses, and this would be a 3+. Okay, all right, you do the others on your own. Now, let's go ahead, and we're at the top of page 3, and we're going to talk about the strength of acids and bases, okay? It is true. There are strong acids and bases, and there are weak acids and bases. Now, it's going to be super important that you know and memorize these strong acids and bases. And whatever is not on your list will consequently be a weak one. So let's go ahead and just talk about what does it mean if something is a strong acid or a strong base. What that means is it is going to completely disassociate into its ions when we put it in water. All right, you can see here from the graphs here that before your disassociation, you have some acid. And you can see that this is an acid, you guys. I can tell because it's starting with a hydrogen. And I believe they're using the letter A for acid. Okay, and what's going to happen here is it is going to completely disassociate almost 100% into its hydrogen protons and whatever anion is attached to it. All right, so when we have this happen, we can assume that the acid is going to fall far to the right, or in other words, it's going to have a very large K value because it is going to almost 100% disassociate into its products, which again are the hydrogen proton and whatever other anion it's attached to. Consequently, you can assume that weak acids and bases are going to behave in just the opposite. Now, weak acids and bases are not going to disassociate very much. In fact, it is assumed that just under 1% of a weak acid or weak base will actually disassociate into its ions, okay? Now, mainly it sits together and remains intact. And so, of course, this would be a double arrow here. This would also mean that the K value, the equilibrium constant, would be very small, okay, or less than 1, okay? Now, when we talk about the K values or the K constants, the equilibrium constants, when we talk about acid and base chemistry, we're now going to call them Kas and Kbs. And of course, the Ka is the acid and the Kb would be the equilibrium constant for bases, okay? As we go throughout this unit, please do not confuse concentration with strength. Just because an acid is a strong acid doesn't mean it is highly concentrated. It simply means when we talk about strength, you guys, okay, weak and strong, it simply refers to the ability to disassociate in water. One more time, a strong acid and a strong base is going to almost 100%, not quite, but almost disassociate into its ions. And a weak acid and a weak base is going to do just the opposite. Again, basically about 1% of the weak acid or base will really only separate into its ions. So it's necessary to have that double arrow because most of our substance is still intact. Okay, all right. Page 3 and page 4 is basically just going to tell you what the strong acids are and what the strong bases are. I think this is something that you could do on your own. We will also talk about this in a little bit more detail in class, as this video is already running longer than I wanted to. So why don't you go ahead and identify the strong acids and the strong bases. And that's going to bring us to the bottom of page 4. One more thing, you do have to memorize these. And again, we will touch base on these in class in a little bit more detail. Okay, thank you so much for watching.